In 1963, Richard Feynman gave an unsettling answer. It is important to realize that in physics today, we have no knowledge of what energy is. He did not mean that physics knows nothing useful. He meant that no one has identified a concrete thing and shown, this is what energy really is. Ask a classroom what energy is, and the answer instantly explodes into adjectives: kinetic, thermal, chemical, electrical, gravitational, nuclear, radiant, elastic. We have a name for almost every place where energy appears. But remove every adjective. Leave only the noun. What is energy itself? We measure energy in joules. We calculate it with extraordinary precision. We predict how much motion, light, heat, or mass can emerge from a process. But knowing every rule followed by a quantity is not necessarily the same as knowing what that quantity is. Begin with a pendulum. At its highest point, the bob is momentarily at rest. Its speed is 0, so its kinetic term is 0. Relative to the lowest point, its height is h, so its gravitational potential term is mgh. Release it. As the bob falls, its height decreases and its speed increases. The number mgh becomes smaller while 1/2 mv squared becomes larger. At the bottom, the kinetic term is largest. The total, k plus u, remains unchanged in the ideal pendulum. Real pendulums slow down. The mechanical total seems to disappear, but the pivot and the air warm by a tiny amount. Motion has been distributed among microscopic degrees of freedom. We now call that part internal or thermal energy. Include the surroundings, and the wider total still balances. This reveals what the adjectives really do. Kinetic, gravitational, elastic, chemical, and thermal are columns in one accounting system. They tell us which variables to inspect and which formula to use. They are not differently colored fluids made from different kinds of energy stuff. Heat makes the redistribution visible. Particles in the hot region have greater average kinetic energy, particles in the cold region have less. Remove the boundary, and collisions transfer energy step by step. The fast population slows while the cold population speeds up. The total energy in the closed box remains constant, but its spatial distribution becomes uniform. Heat propagation is a chain of microscopic events, not a new material fluid. Nuclear energy sounds as if it must reveal a deeper essence, but it also records a difference between physical states. A bound nucleus can have less mass than its separated ingredients. The released energy is the initial mass minus the final mass multiplied by c squared. The calculation is profound. The noun remains unexplained. So the same word survives every transformation. Motion can become heat. Chemical change can become light. Nuclear binding can become motion and radiation. The adjectives change because our description changes. The conserved numerical account is what connects them. The strongest universal statement is therefore not a picture, but an equation. For an isolated system, energy before equals energy after. This is an extraordinarily powerful constraint. It tells nature what totals are allowed, but by itself, it does not describe a hidden mechanism called energy. Feynman illustrated the problem with indestructible blocks. Imagine that a child always owns 28 blocks. When one disappears into a closed box, we invent a weighing rule to infer the hidden block. When blocks hide somewhere new, the accounting rule becomes more elaborate. The total remains 28, even though we never see a substance named totalness. Modern physics can go one important step deeper. Repeat a closed experiment now, then shift the entire experiment 1 hour into the future. If the fundamental rule has not changed merely because the clock reads a different time, the system has time translation symmetry. Noether showed that this symmetry produces a conserved quantity. Let Q describe one coordinate of a system, and Q dot its rate of change. The Lagrangian, L, summarizes the dynamics. Define E as Q dot times the derivative of L with respect to Q dot minus L. Now differentiate E with respect to time. Two acceleration terms appear, one positive and one negative. They cancel exactly. What remains contains the Euler-Lagrange equation, the equation obeyed by the actual motion. That bracket is 0. The result is simple. The rate of change of E equals minus the explicit time derivative of L. If the rule L does not explicitly change when we shift the clock, that derivative is 0. Therefore, the rate of change of E is 0. Time symmetry gives energy conservation. For an ordinary particle, L is kinetic minus potential energy. Substitute that expression into Noether's definition. The algebra returns 1/2 mv squared plus v. The familiar kinetic and potential terms are not guessed separately. Together they arise as the conserved quantity associated with time symmetry. But notice what the derivation did and what it did not do. It explained why a calculable quantity remains constant when the laws are unchanged in time. It did not reveal a material object called energy. Symmetry gives a structural answer, not a picture of an underlying substance. Quantum mechanics sharpens that structural answer. In the Schrödinger equation, the Hamiltonian H is the energy operator. H generates the change of a quantum state through time. In this precise sense, energy is not merely conserved. It is the mathematical generator of temporal evolution. Relativity places energy and momentum inside one geometric object, the four momentum. Its invariant length gives E squared over C squared minus P squared equal to m naught squared C squared. Multiply by C squared and move the momentum term to the other side. We obtain E squared equals m naught C squared all squared plus PC squared. Here m naught is the rest mass. The rearranged equation can be drawn as a right triangle. One leg is rest energy, m naught C squared. The other is momentum energy, PC. The hypotenuse is total energy, E. At rest, P is 0 and E is m naught C squared. For a photon, m naught is 0 and E equals PC. The drawing is Euclidean, but the invariant from which it came is Minkowskian. Now make Pythagoras dynamic. In a 3-4-5 example, the squares on the legs contain 9 and 16 equal units. Imagine those units as a fluid of spacetime interaction events. Poured together, they exactly fill the 25 units of the hypotenuse square. This conserves area and makes the algebra visible. It is an intuition, not an established identification of energy with a literal fluid. During a physical interaction, particles can enter, collide, and leave in completely different directions. What remains equal is the total form momentum. The sum of all energies before equals the sum after, and the vector sum of all momenta before equals the vector sum after. The events and directions are redistributed, the invariant account survives. This is the deepest answer physics currently has. Energy is the conserved charge associated with time translation and the generator that moves physical states through time. Thermal, nuclear, kinetic, and gravitational tell us where the account is written and how to calculate it. They do not tell us what energy is in itself. Feynman's point survives. Nature can change motion into heat, bonds into light, and mass into radiation while preserving an invisible number. We understand that bookkeeping with astonishing accuracy. We still do not know what, if anything, the bookkeeping is ultimately counting.